Welcome back to the Deep Dive. Today, we are putting on our architect hats and walking straight into the fire. We're tackling the 3V0-25.25.
Yeah, the VCAP. That combination of numbers and letters, it strikes a bit of fear into the hearts of even seasoned virtualization admins.
It really does. And for everyone listening, we're talking about the VMware Cloud Foundation VCF Advanced Professional Exam. And I want to be super clear right off the bat. If you're listening to this, we assume you already know your way around vSphere and NSX. This is not an entry-level chat.
No, not at all. This exam is a different beast entirely.
It is.
Completely. The VCP, the Certified Professional level, that validates that you can operate the car. You know where the brake is. You know how to turn on the wipers.
Right.
The VCAP, which is what the 3V covers, validates that you can build the car from scratch, engine and all, while it's moving down the highway at 80 miles an hour.
And the stats back that up. I was looking at the exam blueprint this morning. You have 60 questions, a rigid 135-minute time limit, and a price tag of $250. It's high stakes.
It is. And you need a scaled score of 300 to pass. And frankly, you do not get there by guessing.
No way.
No, you don't. And the biggest mistake I see people make with this specific exam is thinking they can just memorize the admin guide. This is a design and integration exam.
It's about decisions.
Exactly. It tests your ability to make decisions, often between two options that both look correct, but one is more correct for the VCF architecture.
It's all about the why. So here's our mission for this deep dive. We've got a stack of practice questions from the source material. But instead of treating this like a quiz show where we just read the answer key,
which would be boring.
Super boring. We're going to reverse engineer the architecture. We're going to look at why VCF forces you down certain paths for networking, for security, and for resilience.
I like that approach. We need to dissect the logic. Because if you understand the logic of the platform, you don't need to memorize the answers.
It's become intuitive.
Exactly.
Okay, let's get into it. I want to start with the plumbing, connectivity. Because let's be honest, you can build the sleekest SDDC in the world. But if it can't talk to the outside world, it's just a very expensive space heater.
Connectivity is always where the hardest design decisions happen, especially in these hybrid environments.
Right. So let's look at a scenario from the source material. You're tasked with connecting your VCF networking to a public cloud provider, AWS, Azure, whatever. The big requirements are scalability and dynamic routing. The exam gives you a few VPN choices: policy-based, layer 2, or root-based IPsec.
And this is a classic gotcha because, a lot of legacy setups still use policy-based VPNs. But for VCF, and specifically for this exam, the answer has to be root-based IPsec VPN.
Okay, let's unpack that. I know from my own experience that policy-based VPNs are a nightmare when things change. You have to match those interesting traffic access lists on both sides perfectly.
Exactly. It's brittle. Every time you spin up a new subnet or add a new tenant segment in your VCF environment, what do? You'd have to manually log into the firewall, update the policy, then call the cloud team and have them update their side. In a dynamic cloud environment, that is it's operational suicide.
So the root-based option wins because?
Because it uses virtual tunnel interfaces, BTIs. But the real key here and what the exam is looking for is the support for BGP.
The Border Gateway Protocol.
Right. With root-based VPNs running BGP, your VCF edge and the public cloud gateway are constantly talking. If you add a network, BGP advertises it automatically. The routes they populate dynamically. It takes the human error out of it.
That makes total sense. You're building for scalability. If the network changes, the routing just adapts. No change ticket needed. But speaking of adaptation, let's talk about failure, because fibers get cut.
It's not a matter of if, but when.
So true. The source material brings up a specific resiliency scenario with BGP peering. We just said we're using BGP, but if a physical link snaps, literally the backhoe goes through the fiber standard. BGP can be painfully slow to notice.
Painfully is the right word. Standard BGP hold timers are often set to, 180 seconds by default. That means if the link goes silent, your router might keep sending traffic into that black hole for 3 full minutes.
3 minutes is an eternity.
It is.
In any modern environment, that's a total service outage. So the question asks about the benefit of enabling BFD bidirectional forwarding detection.
BFD is the adrenaline shot for your routing protocol. It is absolutely essential in a VCF design. The answer the exam is looking for is faster detection of physical link failures.
How much faster are we talking here in a VCF context?
We're talking sub-second, millisecond.
That is a massive difference.
It changes the game completely. BFD sends these rapid-fire hello packets. The moment they stop, BFD kicks the BGP session and says, tear it down now. The routing table updates immediately. Users might see a screen flicker, whereas without BFD, they're calling the help desk.
So for the exam, BFD equals resilience. Got it. Now let's move down the stack a bit to the virtual machines themselves. We have a scenario about IP address management.
Ah, the classic IPv4 address shortage, a tale as old as time.
It is. The scenario paints a picture where you have a fleet of internal VMs, maybe web servers needing updates, right? And you have exactly one public IP address from your ISP. The question asks which type of NAT handles this.
This should be muscle memory for most network engineers, but in VCF terms, we're talking about source NAT. Or SNAT.
Right. I think we all get the basic concept that many internal IPs hiding behind one public IP, but why is this specific distinction important for the exam? Why not DNAT or one-to-one?
It's all about directionality and conservation. Destination NAT, or DNAT, is for when you want the world to reach into a specific server. One-to-one consumes a public IP for every single VM, which is just wasteful. SNAT is specifically for that outbound flow where the source is internal.
It's the standard pattern for a private subnet.
Exactly. In VCF, you configure this on your Tier 0, Tier 1 gateway. It translates the source IP of the packet as it leaves the SDDC. So the return traffic knows how to get back to the gateway, which then routes it back to the specific VM. It's vital.
Okay, so we've established the plumbing. We have a dynamic pipe with route-based VPN, a safety net with BFD, and efficient outbound access with ZAT. Now, I want to shift gears to the structural design of the VCF itself. This is where I feel the exam separates the people who know old VMware from the modern VCF architects.
You're talking about the switching architecture, I assume?
I am. There's been a significant evolution here. The source material has a question explicitly asking about the switching architecture used in a modern VCF deployment.
This is a huge pivot point. For a few years, we were living in the world of the NVDS, the NSX virtual distributed switch. And honestly, it was a bit of a headache.
It was. You had to manage your standard vSphere distributed switches for your management traffic, and then this totally separate NVDS for your overlay networking. It was complex.
It fragmented the management plane. The exam wants you to know that the new standard, the modern way, is the converged VDS.
Converged VDS. So we were putting the toothpaste back in the tube.
In the best way possible, yeah.
Yeah.
With VCF 4 and 5, NSX can now run directly on top of the standard vSphere distributed switch. You don't need a separate switch for NSX anymore.
That sounds like a massive simplification for the architect.
It is. It reduces the complexity of your uplink configuration, it saves physical ports, and you can manage everything through the familiar vCenter interface. If you answer NVDS on the exam, you're referencing an outdated architecture. Converged VDS is the answer.
Good to know. Don't be the dinosaur in the room. Now, let's talk about where the heavy lifting actually happens. We talk about these gateways, Tier 0, Tier 1, but they're just logical constructs. They're software. They have to live somewhere.
Correct. And this is a concept that trips a lot of people up. You can draw a Tier 1 gateway on a whiteboard, but if you don't assign it compute, it can't actually process packets.
The specific question focuses on stateful services, things like load balancers, NAT, or gateway firewalls. If I configure a Tier 1 gateway with a load balancer, where is that service instance actually running?
The answer is on an edge node within an edge cluster.
Why specifically the edge node? Why doesn't it just run on the hypervisor on the host where the VM lives, like the distributed firewall does?
That is the critical distinction. Distributed services like microsegmentation, they run in the kernel of every host. But stateful services need a centralized point to maintain the state of the connection. They need to know that packet A came before packet B. You can't distribute that easily. So VCF funnels that traffic to the edge node.
So the edge node is the aggregation point for these heavy services.
Exactly. It's the muscle of the network.
But that creates a scary scenario. If all my critical NAT and load balancing is happening on this one edge node, what happens if I need to patch it?
Now we're getting into high availability HA.
The source material presents a scenario that every admin dreads. You have an active standby edge config. You need to put the active node into maintenance mode for an upgrade. The question is, what happens to the traffic?
If you designed it right and VCF handles this out of the box, the answer is traffic gracefully fails over to the standby node.
I want to double-click on gracefully, because in the old days, failover meant
everyone's connection drops and they have to log back in.
Yeah.
That's not acceptable anymore. In this active standby model, The edge nodes are constantly syncing their connection state tables. The standby node knows about every open TCP session that the active node is handling.
So when I hit enter maintenance mode,
The system triggers a failover. The standby node promotes itself to active, sends out a gratuitous ARP to the physical network saying, hey, I own this IP now. And it picks up the conversation right where the other node left off.
so if I'm on a Zoom call routing through that edge, I don't get disconnected.
You might see a tiny jitter, maybe lose one packet, but the session stays alive. The application doesn't crash. That is the definition of graceful.
That's the kind of assurance you need when you're hitting that upgrade button at 2 in the morning. Okay, section 3. We have covered the plumbing and the structure. Now I want to talk about the rules of the road. Governance and control.
This is where we keep the network from descending into chaos.
Let's start with routing hierarchy. We have the tier 0 on top, talking to the world. Tier 1 is below it. If I create a new network segment on my tier 1 gateway, does the tier 0 automatically know about it?
No, it does not, and that's by design.
Okay. The question asks what feature must be enabled to fix this.
The answer is read advertisement.
Walk us through the logic there. Why isn't it automatic?
Multi-tenancy. You might have 10 different tier 1 gateways for 10 different tenants. You might not want all their internal networks exposed to the tier 0 or the outside world. You might want some to be isolated. So, by default, the tier 1 keeps its mouth shut.
So rude advertisement is the tier 1 effectively raising its hand.
That's a great way to put it. You have to explicitly configure the tier 1 to advertise its connected segments and static routes up to the tier 0. Once you flip that switch, the tier 1 tells the tier 0, hey, send any traffic for these subnets down to me. Without that, the tier 0 just drops the traffic.
It's about explicit control over what's reachable. Speaking of control, let's talk bandwidth.
Quality of service, QoS.
Yep. The exam has a specific question about where gateway QoS is applied. The answer is on the gateway uplinks.
I feel like a lot of people might guess on the VM interface or on the logical segment. Why is the correct answer the uplinks?
Think about where the bottleneck is. Inside your VCF instance, your east-west traffic between hosts is running on, 25 gig or 100 gig links. It's a superhighway.
It's too fast to clog up. Exactly. But the uplink, that's your exit ramp to the WAN or the internet. That bandwidth is expensive and finite. That is where you have the noisy neighbor problem.
The person downloading a 50 gig patch file while the CEO is trying to do a video conference.
Precisely.
Mhm.
So you apply QoS on the gateway uplinks, usually at the tier 0 or tier 1 level, to police that north-south traffic. You classify the critical traffic, give it priority, and you throttle the bulk traffic. Applying it internally is usually just a waste of CPU cycles.
Focus on the choke point.
Oh.
Got it. Next up, let's talk about the humans. Role-based access control, or RBAC.
Security is everyone's job, but not everyone should have the keys to the kingdom.
The scenario here is classic enterprise friction. You need a user who can manage firewall rules, the security posture, but you are terrified of them messing up the routing, deleting a gateway, or breaking the topology.
Yeah, you need to keep the security guy away from the networking guy's toys.
Exactly.
This is a strict separation of duties. The VCF role for this is the security administrator.
It sounds obvious, but the nuances of the permissions are what matters here.
Right. The security admin can edit the distributed firewall, the gateway firewall, and security groups. They can lock the doors, but they cannot move the walls. They can't change IP addresses, they can't change BGP peering, and they can't delete segments.
Which protects the infrastructure from well-intentioned accidents.
We've all seen them. RBAC prevents that. It ensures the person writing the policy isn't the same person building the pipes.
One last topic, and it's one that I think brings the most relief to admins who have managed legacy environments. Certificates.
Oh, the silent killer.
SSL certificates expire. It's just a fact of life. In the old days, if your NSX manager certs expired, you were logging into 3 or 4 different appliances, generating CSRs. It was a manual, error-prone mess.
And if you missed one or pasted the key wrong, the whole cluster broke.
The question asks, which component automates this in VCF?
The hero of the story, SDDC Manager.
We haven't talked much about SDDC Manager yet, but it's really the brain of the whole operation, isn't it?
It is. SDDC Manager is what makes VCF a platform rather than just a bundle of products. For certificates, it acts as the central authority. You can tell SDDC Manager to rotate the certificates for your entire NSX cluster or vCenter, and it just handles the workflow.
So it logs in, replaces the cert, restarts the services, and validates everything.
All automated. It turns a 4-hour high-stress maintenance window into a click-and-monitor task. It ensures compliance.
That is the power of automation. We covered a lot of ground today, from the edge of the network to the core of the SDDC. Hopefully this helps you not just pass the 3V0-25.25, but actually enjoy building these VCF environments.
It's great tech when you understand the design intent behind it.
Thanks for tuning in. Stay curious, keep building, and we will catch you on the next deep dive.